Okay, so the next question that we have here is question number 8. The question is, let A and B be sets. Okay, now we want to show that basically f as a function from A, the Cartesian product of A and B, to another set which is the Cartesian product of B and A, such that A comma B is equal to B comma A is a bijective function. Is a bijective function. Okay. Now, in order to understand this situation, first of all, basically you have A and B, you have two sets here. And basically you have this set A and this set B. And you have two sets based on these two sets. The first set, which is your domain, is the Cartesian product of A and B, and the second set, which is your codomain, is the Cartesian product of B and A. And you know what the Cartesian product of two sets actually means. For example, if you have, let's say that A is equal to, for example, these sets A1, A2, A3, and A4, and if B is equal to, for example, B1, B2, B3, and B4, then the Cartesian product of, or let's make this a little bit simpler. Let's go all the way up to 3 only, right? So if you have basically A is equal to A1, A2, A3, B is equal to B1, B2, B3, then the Cartesian product of A and B is going to have, since each of these has 3 elements, then the Cartesian product of A and B is going to have 3 times 3, which is equal to 9 elements, which would be basically A1 comma B1, which would be A1 comma B2, A1 comma B2, which would be A1 comma B3, which would be then be A2 comma B1, A2 comma B1, and then you have A2 comma B2, and you have A2 comma B3, right? And then, oh sorry, I wasn't supposed to close that. And you have A2 comma B3, then you have A3 comma B1, A3 comma B1, you have A3 comma B2, and you have A3 comma B3, A3 comma B1, B2, and B3. So this is going to be the Cartesian product of A and B. So you can see that these are all the ordered pairs that you can form from these two sets. The first basically element is going to be from the set A, the second element is going to be from the set B, and that is the Cartesian product of A and B, meaning that A times B. And you can see that A comes first here, B comes second here. Now in the same based on the same situation, the Cartesian product of B and A, which is B times A, is basically, well, B1 comma A1, you have B1 comma A2, and you have B1 comma A3, then you have B1, basically B2 comma A1, B2 comma A1, then you have B2 comma A2, and then you have b2 comma a3, right? And then you have b3 comma a1, then you have b3 comma a1, then you have b3 comma a2, and then you have b3 comma a3. And that is going to be the Cartesian product of B and A. As you can see, you get 1, 2, 3, 4, 5, 6, 7, 8, 9 ordered pairs here. In each ordered pair, the first element is from the set B, because B comes first here, and the second element comes from the set A here, right? Now, basically what we are saying here is that basically you have such two, basically it doesn't really matter the size of the two sets. Now we have taken, for example, that A has 3 elements and B has 3 elements, and then depending on the number of elements of A and B, then you would get a more number of such ordered pairs in each of these two sets. Now what we are saying is that we want to show that basically f, which is a function from this set A times B to this set, which is B times A, such that A comma B is equal to B comma A, right? A comma B is equal to B comma A. That means that, for example, this ordered pair over here, A1 B1, is equal to B1 A1. A1 B2 is equal to B1 A2. I'm sorry, A1 B1 and again over here I have B1 A1. Where is B1 A1? So okay, so A1 B1 and B1 A1 based on this rule are going to be equal, and then you can say that basically A1 B2 is the same thing as B2 A1, which is this one over here. So that means that, for example, this A1 B2 is the same thing as B2 A1. A1 B1 is the same thing as B1 A1, or basically A1 B3 is the same thing as B3 A1, for example. A1 B3, B3 A1, and so on and so forth, right? So we want to show that this is this function. We want to show that this function is a bijective function. Okay, so basically in this situation you can see that, first of all, in order to show that f is basically injective, basically f is injective means that every distinct element of the domain has a distinct element of the range of the function as its image. And based on this rule, you can see that we are saying that A comma B is the same thing as B comma A, meaning that for example, suppose you take A1 comma B1. So the only element in the codomain that this element can be mapped to would be basically A1 comma B1. This can only be mapped to this element over here. There is no other element that this can be mapped to based on the rule that we have here. Moreover, for example, any other element that you take, for example, A1 comma B2, A1 comma B2 can be mapped to B2 comma A1, and no other element here. That means that every element that you pick in the domain of the function will have a distinct image in the codomain of the function. and so your function is injective. So what that means is that your function is injective. Now in logical terms, the same argument you can write it as okay, so to write basically the same argument in logical terms, let's say that basically we know that f is a function. F is a function from a times b to b times a, defined as basically f of, as we can see here, f of a comma b is equal to b comma a. F of a comma b is equal to b comma a. Right? So now, based on the definition of this function, let us assume that, and since we want to show that basically f is, we want to show that f is objective, not objective but injective. F is injective, meaning that we want to show that the statement for every x1 comma x2 belonging to x, f of x1 is equal to f of x2 implies that x1 is equal to x2. We want to show that this condition is true for the function f. So now, in order to do that, what we need to do is that let us assume that f of x1 is equal to f of x2. Let us assume that f of x1 is actually equal to f of x2, which means that in this particular case, you can imagine that you can assume that let us assume that, for example, some a1 b1 and some a2 b2, for example, belong to the domain of this function, which is the Cartesian product of a and b, such that basically I want to just simply create this condition, this situation, such that f of this is equal to f of this, meaning that f of x1 is equal to f of x2. So I'm taking this as my x1, I'm taking this as my x2, right? Such that f of basically a1 comma b1 is equal to f of a2 comma b2, right? Now, what this implies is that, so here basically we said that f of a comma b is b comma a, meaning that you just swap the places of a and b, and you will get the output of your function. So this statement over here means that basically b1 comma a1 is equal to b2 comma a2. Now this is an ordered pair, so you know that in an ordered pair, basically two ordered pairs are equal if and only if the first element is equal to the first element in the first ordered pair is equal to the first element in the second pair, and the second element in the first pair is equal to the second element in the second pair, meaning that this statement is true if and only if basically b1 is equal to b2 and a1 is equal to a2, right? So if that is the case, then that means that your statement is true. Now, and of course, since we have assumed that this is true, then based on my assumption, this is true and this is also true, meaning that B1 is equal to B2 and A1 is equal to A2. Which means that basically A1 B1 is equal to A2 B2, right? So this means that A1 comma B1 is the same thing as A2 comma B2, or they are equal, because A1 is equal to A2, the first element here is equal to the first element, and B1 is equal to B2. Basically, the second element is equal to the second element. That means that these are equal. So here what we have shown is that f of A1 B1 is equal to f of A2 B2 implies that A1 B1 is equal to A2 B2, and therefore you can say that f is injective. F is injective, or basically 1 1. That is basically the logical way of saying the same thing that I said in a couple of sentences. Of course, this is a much better way of saying the same thing, and perhaps it's a little bit more, it's not as easy to understand, but well, of course, mathematically, it's what I said must be expressed this way, otherwise it's not mathematically correct. Yeah, I mean, the statements that I used in the before this set of arguments were just a bunch of sentences. They were logically correct, but well, I'm not really sure if you couldn't find something logically not wrong with that, or with some of those sentences at least. So there is always the possibility that you could find some fault in your logic when you're just loosely using language and some senses in order to put something together. But then when you write it in the form of a proof, then nothing can really go wrong. If there is something wrong, algebra will show you your own mistake, right? So that is basically the first part. The second part, you want to show that f is basically surjective. And what that means is that every element of the codomain of the function, which is basically the Cartesian product of b and a, is the image of some element in the domain of the function a times b, right? So in order to do that, the argument that you can use is that basically let b comma a. So over here, basically we said that f is a function defined as f of a comma b is equal to b comma a, right? So you can so I can say that now let b comma a belong to the Cartesian product of b and a, meaning that to the codomain of the function, belonging to this set, be any element, any typical element of the codomain of the function, right? Now then you can argue that since we know that basically f of a comma b is equal to b comma a, and b comma a is basically the output of the function, then there exists a comma b belonging to the set, the Cartesian product of a and b, such that f of a comma b is equal to b comma a by, of course, by the definition of the function, right? And therefore you can say that f is onto or surjective, f is onto or surjective. And so what this means is that based on the definition of the function f of a comma b is equal to b comma a, then there exists, and if I assume that b comma a is any element in belonging to the domain of the function, belonging to the codomain of the function, then of course, as you can see, there is always the possibility that meaning that any typical b comma a is covered in this relationship, because for any b comma a there exists some a comma b such that f of a comma b is equal to b comma a. That means that any b comma a is the image of some element in the domain of the function, right? And therefore f is onto, meaning that there is no element in the codomain of the function, which is this set over here. There is no element here that will be left alone. Every element that you can see here will be the image of some element in the domain of the function. And what that also means is that basically the codomain and the range of the function are going to be equal sets, right? So that is basically that. And so hence you can say that f is onto or surjective, and since we showed that basically f is injective and also surjective, then you can say that basically f is bijective. And I have said this before as well, but you can see injective and surjective means basically 1 and onto, right? Now the word bijective does contain the part bi. Bi means two. So the way that I have learned this, which works for me, is that basically bijective does basically include the part which is injective and also surjective, meaning that it does include two cases. But then injective or surjective, well, injective is just injective, surjective is just surjective, but bijective is both of them together, right? Or if it's easier for you, you can learn one and onto, but then I suppose you need to know all of the words, otherwise you would get confused. So that was question number 8. Now the next question that we have here is question number 9, which is a little bit more complicated than the cases before, but we will get through that as well. Okay, so now about question number 9. Basically, we have, let f be a function. We have f as a function from n to n, which is defined by basically f of n is equal to basically n plus 1 divided by 2 if n is odd. If n is odd, and n divided by 2 if n is even, right? For all n belonging to n. For all n belonging to the set of natural numbers. You want to know whether this function is bijective or not, meaning that you want to know whether it is injective and also surjective. If it is both injective and surjective, then it's bijective. Now, for the part to show that it is injective, basically what you want to do here is that well, there is actually two ways to do this. I have solved this problem in two different ways, or at least I know two different solutions. So first, you can show that basically, first of all, f of 1 here is equal to, if n is odd, so basically you basically use this part of the function, which is n plus 1 divided by 2. So 1 plus 1 divided by 2, which is equal to 2 divided by 2, is equal to 1. Also, f of 2 is equal to, if n is even, you use this part of the function, which gives you 2 divided by 2, which is equal to 1. So you can say that, you can see that basically f of 1 is equal to f of 2 is equal to 1, and of course 1 is not equal to 2. And we said that for every a1 and for every a1 and a2 belonging to the domain of the function, if f of a is equal to f of a1, for example, is equal to f of a2, then that should imply that a1 is equal to a2. And you can see that over here, and that means that the function is injective. And here you can see that f of a1 is equal to f of a2 is equal to 1, but a1 is not equal to a2, so of course then you can say that the function is not f is not injective. So that is one part. Or you can say that basically there is basically you can solve this problem in another way. You can say that, let's suppose that let's make the assumption that f of a1 is equal to f of a2. This is another solution for the same thing exactly. This is another solution for the same thing. So you can say that, let's suppose that, assume that f of a1 is equal to f of a2. Okay? If that is the case, then there are a couple of different cases. So a1 and a2 basically represent the different inputs of the function. So the inputs of the function could be even or odd. So there is case 1. There is case 1 where a1 and a2 are both, for example, even. There is another case, case 2, where a1 and a2 are both, for example, odd. There is another case 3, you could say, where a1 is, for example, even and a2 is odd. And there is another case, let's call it case, for example, case 4, where a1 is odd and a2 is even. So now we can consider all of these 4 different cases. For the case where, for case 1, if a1 and a2 are both even, then you can use this part of the function f of n is equal to n divided by 2. F of n is equal to n divided by 2. And so then you can say that f of a1 and f of a2 would be a1 divided by 2 is equal to a2 divided by 2, which means that A1 is equal to A2, which means that basically F is injective. F is injective. Now, since F is injective in this case, case number two, we said that both A1 and A2 are odd, which means that I have to use this part of the function, n plus 1 divided by 2. So here basically you have f of n is equal to a plus 1 divided by 2, or I'm sorry, n plus 1 divided by 2, which means that then f of a1 is equal to f of a2. The assumption is f of a1 is equal to f of a2, which means that based on the formula that we have here, that gives me a1 plus 1 divided by 2 is equal to a2 plus 1 divided by 2, and then you can basically multiply both sides by a factor of 2. You will get a1 plus 1 is equal to a2 plus 1, and then you can simplify these two, and then that gives you a1 is equal to a2, which means that basically f is injective, right? So that is case 2. Now case 3, you can say that for case 3, which is basically a1 is even, a2 is odd. So for the even part, we said that f of n is equal to n divided by 2 for n even, and for the odd part, we said that f of n is equal to n plus 1 divided by 2 for n odd. Now here I'm assuming that a1 is even, a2 is odd, and the other assumption that I've made is f of a1 is equal to f of a2, right? So f a1 is even, so that means that a1 divided by 2 is equal to f of a2, and a2 is odd there, so a2 plus 1 divided by 2. a2 plus 1 divided by 2. And of course you can see that you will not get this. You will get a1 is equal to a2 plus 1, and so that means that basically a1 is not equal to a2, which means that basically f is not injective. Now, since you have shown that in one case f is not injective, then you don't have to examine this case anymore. Then you can basically conclude the same thing, that f is not injective, as your final conclusion, right? Now the second part of this problem, you want to show that you want to examine whether f is surjective or not. Is surjective or not. Okay, so now in order to check whether f is surjective or not, well, of course you can use the rules of the function that you have, meaning that you have the rules of the function, you have n plus 1 divided by 2 and then n divided by 2 for odd and even numbers, meaning that if there can be two cases. So basically there can be two cases. So you can basically consider some natural number n belonging to the set of natural numbers, which is basically your codomain, which is your codomain, right? And if that is the case, basically then then you can use then you will have basically two cases there. Case one, you can say that basically either, for example, n is odd, in which case you can use basically this part of the function n plus 1 divided by 2. You can use f of n is equal to n plus 1 divided by 2, and let's call f of n, for example, let's call it m, for example. Let's call it m, for example. That means that m is equal to n plus 1 divided by 2. And so what that means is that 2m is equal to n plus 1, or n is equal to 2m minus 1. Is equal to 2m minus 1. That means that basically for this function, for the function that we have, for every m which is the output of the function, you can say that there is 2m minus 1 that's basically that you can enter into the function to give you basically m, meaning that you can write f of 2m minus 1 is going to be equal to m, because over here you have f of n is equal to n plus 1 divided by 2. And so if I take my input as 2m minus 1, f of 2m minus 1 is going to give me basically 2m minus 1 plus 1, and divide that by 2. These two will be cancelled out. 2m divided by 2 is going to give me m. So that means that every output of the function, every output m of the function, for every m there is 2m minus 1, which will be mapped to that m, or that m is the image of some 2m minus 1 in the function. And whatever the value of m is, let's say that m belongs to the set of natural numbers. Then for whatever m, if you multiply it by 2, you will get a natural number. Subtract a 1 from 1, you will get a natural number. So that number exists in the set of natural numbers, which is basically the domain of your function n. And so there you have, your function is, so based on that you can say that your function is surjective, meaning for every m there is some 2m minus 1 which is also present or available in the domain of your function. And so this m is basically the image of that 2m minus 1, right? Now if you use the other part of the function for the case where, for case 2, where basically n is even, when n is even, what you will have is that basically we said that f of n is equal to n divided by 2. So then again, if I call f of n, if I call it m, for example, then that means that m is equal to n divided by 2, or n is equal to 2m. That means that again, f of 2m is going to be equal to m, as we argued here. And so that means that for every m, or for every output of the function, for every output m, there is some 2m which is basically mapped to that m, or that m is basically, every m is the image of some 2m in the domain of the function, right? And it's important to note here that basically when you get the, so here we are basically simply calculating the inverse of the function, right? So here what's important here is to note that, for example, here I'm saying for every m which is the output of the function, there is some 2m that is basically that is the pre-image of m, or you can say that for every m or you can say that every m is the image of some 2m in the domain of the function. This becomes the domain, and this becomes the codomain, of course. Right? Now it's important to note, it's important to check whether for this, well, we are saying that this m is the image of some 2m in the domain of the function. You need to make sure that this 2m actually does exist in the domain of the function. Otherwise, this doesn't mean anything, right? Or, for example, in this case, you need to make sure for that, we said that basically for every m there is some 2m minus 1, which exists in the domain of the function that is mapped to that m, right? So this is going to help me prove that the function is surjective if that 2m minus 1 can actually exist in the domain of the function. Now, for example, in this case, we argued that let's take m as some natural number. If m is the output of the function, some natural number, then of course, then based on that, any natural number that you multiply by 2, you'll get another natural number. So whatever that might be subtracted 1 from it, again you will get a natural number. So whatever the value of m, 2m minus 1 can exist in the domain of the function, which means that basically the function is surjective, meaning that every m will have some preimage in the domain of the function, and you have no problems. Now again, the same thing over here, you need to understand it. It's just not basically calculating the inverse of the function and just say that for some, for example, x, there is such and such variation of the variable that gets you there, so problem solved. No. You need to make sure that, for example, now I have f of 2m is equal to m, meaning that every 2m that I input into the function, that gives me m, which is the output of the function. Now here what I need to do is that, of course, I know that m represents some output of the function, which is some natural number, right? Now, and I'm saying that basically the input that I need to input into this function to get this m is for every m, it's 2m, meaning that whatever the value m multiplied by 2, that input, it should be input into the function in order to get that output. Now, now this whole argument depends on what sort of range and what sort of domain and codomain you have. So for example, over here, the domain is the set of natural numbers, the codomain is the set of natural numbers. So here, m represents the set of some number in the set of natural numbers. So if m is a natural number, then of course any natural number, when you multiply it by 2, it's still going to be a natural number. That means that it can exist in the set of natural numbers. And of course, since the domain of the function is the set of natural numbers, then that means that any m that you have in the output of the function is the image of some element in the domain of the function, which in turn means that all the outputs, all the elements of the codomain are the image of some element in the domain of the function, which in turn means that no element is left alone in the codomain of the function, meaning that basically meaning that the codomain and the range of the function are equal sets. And so what that means is that the function is surjective, right? So we need to understand the meaning of this whole process. Otherwise, sometimes we just learn some sort of technique or some way of checking. For example, what we usually do, or some people, what they usually do is that they learn that, for example, based on some solution, if you do this, then that means that basically the problem is solved. But then, of course, as you know, in mathematics, you need to understand you need to understand the solution, and of course you need to be absolutely clear about the logic that you have used every step of the way. Otherwise you couldn't really call it mathematics. Mathematics means understanding what you're doing. Okay, so now what I'm going to do is that we have basically 3 more problems here. So question number 10, 11, and 12, we are going to do them in the next video. Let's see you in the next video. And thank you.